in the sense of security, we're usually thinking of resilience to an attacker. There's also a lot of cases where there's not necessarily an attacker, but we would still like to have the system be extremely resilient. So for example, autonomous vehicles, there may not be anybody attacking them just because it's easy enough to make people crash cars, and generally there aren't a lot of attacks against human drivers trying to make humans crash cars. But we do want autonomous vehicles to be extremely robust. We do want air traffic control systems to be extremely robust, even though all the air traffic controllers and all the pilots are trying their best to cooperate. A complicated system with important implications for safety requires that any use of machine learning in this cooperative setting be highly robust. Things like surgery robots. There's presumably no adversary trying to interfere with the surgery, but we'd like the surgery robot to successfully carry out the operation and not harm the patient. It turns out that a lot of the techniques from adversarial machine learning in terms of security can actually help with robustness in the natural setting. You can think of the minimax analysis in the security setting as studying how well the model will perform in the worst case. And if it's going to perform very well in the worst case, we know it will perform at least that well in the more natural, statistically occurring case. We've also seen the development of some verification systems, such as ReluPlex, that were originally developed in the context of verifying that systems are not vulnerable to adversarial examples. And then those have gone on to be applied to systems like air traffic control, even though air traffic control is usually not an adversarial setting. In general, what I would like to do with adversarial machine learning is make an engineering discipline out of machine learning in the same way that we saw distributed systems benefit from study of things like Byzantine fault tolerance. In the context of Byzantine fault tolerance, it was useful to bring in an imaginary adversary and prove that distributed systems would function well, even in the presence of an adversary, because that would mean that they would then function well in natural settings. And I think if we're able to develop those kinds of theoretical tools for machine learning, we'll make machine learning perform better across the board.